What if nearly every safety feature on modern aircraft exists because something once failed catastrophically? This story exposes how aviation accidents never truly end at the crash site. They continue silently inside design labs, certification rules, and cockpit logic. From warning systems to automation behavior, today's safest aircraft are built from past failures that revealed weaknesses no one saw coming. Stay until the end to understand how one accident can quietly reshape every plane built afterward, even across rival manufacturers, and why aviation learns faster from failure than any other industry on Earth. Every aircraft flying today carries the memory of past accidents, not as headlines or memorials, but as engineering choices. Materials were replaced, systems were rewritten, procedures were redesigned, all because something once failed and exposed a flaw no one fully understood at the time. In aviation, crashes do not conclude when debris is removed. They live on inside design reviews, pilot training, and regulatory law. When something goes wrong, investigators do not stop at what happened. They push further, asking the most dangerous question of all. Why was the aircraft capable of allowing this failure to occur? That question is why aviation safety advances faster than any other mode of transportation. When an aircraft crashes, investigations begin with evidence, not emotion. Flight data recorders are decoded. Cockpit voice recordings are replayed repeatedly. Radar tracks, maintenance logs, weather conditions, and crew actions are reconstructed in precise detail. Independent agencies like the National Transportation Safety Board in the United States, the Air Accidents Investigation Branch in the United Kingdom, and France's B lead these inquiries. Their mandate is not punishment, it is prevention. In early aviation history, this philosophy did not exist. Crashes were often blamed entirely on pilots. A mistake in the cockpit ended the conversation. But as aircraft grew faster, heavier, and more automated during the jet age, an uncomfortable pattern emerged. The same accidents kept happening, involving different airlines, different aircraft, and highly experienced crews, different continents, identical failures. That repetition forced aviation to confront a hard truth. If trained professionals kept making the same mistakes, the problem was not just human error. The system itself was setting them up to fail. One of the earliest wake-up calls came from mid-air collisions. For decades, aircraft relied on ground radar, radio communication, and pilots visually spotting other planes. The assumption was simple: the sky is vast, and pilots will see each other in time. That assumption collapsed in 1956 when a United Airlines DC-7 and ATWA super constellation collided over the Grand Canyon, killing all 128 people on board. Public outrage followed, but investigators uncovered a deeper issue. Visual separation was unreliable. Human reaction time was limited. Air traffic control coverage was fragmented. The system could not safely scale with growing air traffic. Aviation responded by shifting responsibility to the aircraft itself. Engineers proposed that planes should detect and resolve collision threats automatically without waiting for human judgment. This idea became the Traffic Collision-Avoidance System, TCAS. TCAS allows aircraft to detect one another using transponder signals. If a collision threat develops, the system issues coordinated commands. One aircraft climbs, the other descends. The instructions are synchronized so they never conflict. After another catastrophic mid-air collision in 1996 over India involving Saudi Arabian Airlines Flight 763 and Kazakhstan Airlines Flight 1907, regulators acted decisively. The FAA and the International Civil Aviation Organization mandated TCAS on commercial aircraft worldwide. Pilots were instructed to obey TCAS commands even if air traffic control issued conflicting instructions. That rule exists because hesitation had already proven fatal. One failure permanently changed how every modern aircraft shares airspace. As collision risks declined, another silent killer persisted. Aircraft were flying directly into terrain while fully controllable. Engines worked, instruments functioned. Crews were conscious, yet the aircraft continued descending until impact. These became known as controlled flight into terrain accidents. Eastern Airlines Flight 401 in 1972 showed how distraction could slowly doom a flight. Others revealed the same pattern during night approaches or poor weather. The issue was not recklessness, it was perception. Pilots were given raw numbers, altitude, descent rate, distance, and expected to mentally combine them under stress. In darkness, clouds, or high workload, that mental model failed. Aviation didn't fix this with better manuals. It changed the aircraft. Ground proximity warning systems were introduced. These systems actively monitor terrain closure rates. If danger appears, the aircraft speaks. Those words were selected after extensive human factors testing. They were designed to trigger immediate action, not discussion. Later systems added digital terrain databases, allowing aircraft to predict danger before recovery became impossible. Visual displays showed rising terrain clearly on navigation screens. Manufacturers like Boeing and Airbus embedded these systems across fleets such as the Boeing 737, 777, Airbus A320 family, and A330. Regulators mandated them after accident rates collapsed. Today, controlled flight into terrain is among the rarest causes of commercial crashes. That progress came from design, not chance. As safety systems multiplied, a new problem emerged. Cockpits filled with alerts. Lights, sounds, and messages competed for attention. Individually, systems worked. Together, they overwhelmed. Several accidents revealed the danger. Crews focused on minor alerts while missing critical failures. Warnings sounded alike. Messages appeared simultaneously. The aircraft was reporting problems, not helping solve them. Engineers responded by redesigning how aircraft communicate urgency. Alert hierarchies were created. The most dangerous warnings override all others. Lower priority alerts wait. Colors were standardized. Red demanded action. Amber warned caution. Green confirmed normal operation. Sounds were differentiated. Messages shifted from cryptic codes to plain language. Boeing introduced structured systems like the engine indicating and crew alerting system. Airbus centralized alerts in fly-by-wire cockpits so priorities were unmistakable. These principles were written into certification rules. They became mandatory. As automation advanced, another risk surfaced. Autopilots reduced workload until they didn't. Accidents revealed that automation failures could confuse pilots at critical moments. United Airlines Flight 173 showed fixation blindness. Air France Flight 447 exposed how unreliable sensor data combined with automation changes could overwhelm crews at high altitude. The aircraft behaved logically. The problem was that the logic was opaque to humans under stress. This forced another permanent shift. Automation had to become explainable. Flight mode displays grew clearer. Transitions between manual and automated control were highlighted. Feedback improved so pilots instantly understood what the aircraft believed was happening. Sensor systems gained redundancy. Instead of trusting one input, aircraft compared multiple sources. When disagreement occurred, the system alerted crews instead of silently choosing a value. These lessons shaped aircraft like the Airbus A320neo, Boeing 787 Dreamliner, and Airbus A350. Regulators required proof that automation supported human understanding rather than replacing it. What the public rarely sees is what happens after investigation reports are released. The changes don't stay confined to one airline or model, they enter law. When accidents expose design flaws, regulators like the FAA and EASA issue new airworthiness requirements. These rules apply to all manufacturers. Future aircraft must demonstrate resilience against the same failures before certification. Engineers must show system behavior during sensor loss, pilot error, and automation disconnects. These tests are no longer theoretical. They are written directly from past crashes. Sometimes the rules reach backward. Older aircraft receive software updates, alert modifications, and revised training requirements. Compliance is mandatory. This is why aviation evolves permanently. A single crash can raise the safety standard for an entire generation of aircraft. Planes built decades later still carry the fingerprints of failures long past. In aviation, mistakes do not vanish, they become regulation. What separates aviation from other industries is enforcement. When a fix works, it becomes law. Manufacturers redesign, airlines retrain, regulators audit, nothing is temporary. Passengers rarely notice this progress. They hear calm alerts, they see clean displays. They trust systems without realizing how deliberately those systems were forged through failure. Behind every warning tone and checklist step is an accident report and a lesson learned the hardest way possible. If this changed how aviation safety is viewed, support the channel. Liking the video helps it reach people who care about how aircraft are truly designed. Subscribe for deep dives into engineering, investigations, and the hidden systems keeping flight safe. And if someone trusts flying without ever wondering why, share this with them. Every safe flight carries a lesson worth knowing.